Welcome to ECE 501B. I'm entitling this session on finite dimensional vector spaces Dimension. We'll try to establish notation and terminology, get you reminded of what we mean by some of the phrases or words that we will be using. We will also try to develop insight into these different terms, namely span, spanning list, and dimension. We'll work some examples dealing with dimension, and we'll also then finish up this session by stating some properties of dimension. What I want to do is quickly go through some notation and terminology just to make sure that we're all on the same page. And for that reason, I'm simply going to scroll through some pre-written down pieces of information. First off, the definition of length. You can find that on page 4, the very first part of Axler, and that is listed in a sentence. A list of length n is an ordered collection of n objects. Another piece of information is a list is finite. Examples of lists, you might have the first list here is a star, a square, and a circle. That would be a list. It has a finite number of objects in it. It actually has a length of 3. There's 3 different objects in that list. The second example are 2 vectors. So the length of that list is 2. It has 2 unique vectors. The list doesn't have to have unique elements. Another example of a list would be v sub 1, v sub 2, on up to v sub n. And we really sort of overuse this notation, but hopefully it will be clear from the context. You could see me use this in A as a list of n vectors, where you could think of each of these v1, v2, and v sub n actually representing a vector object. Or I might have this list v1, v2, v sub n, where the different v's are actually maybe just elements of a scalar field, and in that case this is representing a vector with a list of n coordinates in that particular list. The other thing that I want to point out in terms of talking about different objects, a list is not equal to a set, and you can go to the bottom paragraph in Axler on page 4 where he starts to try to explain this distinction between what he is using to define lists and what typically is done for sets. Hopefully that is clear. Let's now look at developing a little insight into these phrases or terms: span, spanning list, and dimension. And when we say spanning list, we're really referring to a set of vectors that span the whole space. To establish that, suppose that we look at this vector space, three-dimensional space, the ordinary three-dimensional space. Let's say that we're dealing now with these examples coming from V, the vector space V. Our first example shows us that what we're meaning by span. If we say the span of this list, and in this case the list is of length 1, it has simply one vector object in it, and that particular object is capable of producing the x-axis. That's what we're meaning by this curly bracketed expression or notation, and I sort of overuse or use interchangeably this notion of a column vector and a row vector, but hopefully it's clear. And when we start representing these as relative to matrices, we'll have to get a little bit more specific on what we are indeed talking about in terms of a column vector or a row vector. The second example, relative to a span in three-dimensional space, now I have a list of 2 vectors. Those vectors are actually linearly independent, and obviously they're unique. In this case, the span is the xy plane, and that's what's represented by the expression on the right. Let's look at another connection of connecting spanning list, and eventually dimension. But this will help us with this concept or this idea of length also. Let's define three different lists. We have a list W that has a length 3. We have a list U of vectors. That list contains 5 different vectors, so that length U is 5. V also is a list of 3 vectors, so the length of V is 3. In all three of these cases, we can see that the span of W is all of V. U, that list, spans all of V, or this three-dimensional space, and V also spans all of V, or R3. And U and V are pretty close, but they are a little bit different. If you look at the first object in that list of 3 in each set, in each list, you'll see that that's a little different, but they both go ahead and span all of R3. So that's what we say when we say spans. W spans V, U also spans V, V spans capital V, and W, U, and V are all spanning lists, meaning all three of those lists span the entire vector space V that they are a part of or that they are contained within. However, they don't all three represent a basis. If you go back and look at those three different sets of lists, it should be clear that W is a basis. There's 3 linearly independent vectors in that list. They span all of R3, and consequently they form a basis. U has some linear dependency among the objects in its list, and for that reason, because they are not linearly independent, U does not form a basis of R3 or V, and V, lowercase v, I maybe am overusing my terms, so I need to be a little bit more specific. The list lowercase v does indeed form a basis because those vector objects in the list are linearly independent. They span all of capital V, or R3, and so V is also a basis for V. Can we use this terminology then to help us start talking about dimension? It would help to actually introduce a new term, and that term is dimension. And before we do that, what really seems reasonable in terms of the definition of dimension? It would be reasonable if we said that the dimension of R to the n, or this n-dimensional space, had a dimension of n, or that it equaled n. And that would match or be consistent with the terminology that we've been using all along. For example, the three-dimensional space R3, we would say that has dimension 3. Also, the standard basis of R to the n is of length n, and you can look at that in this list of vectors, e sub 1, e sub 2, on up to e sub n. That list contains n vectors, and they are linearly independent, and because of that list being linearly independent and spanning all of R to the n, that forms a basis, and it would be nice if that particular space, R to the n, had dimension n. And that's true if every basis on our finite dimensional vector space V had the same length, and we're assured of that by Theorem 214 in Axler. Theorem 214 says any basis of a finite dimensional vector space, and I'm going to subsequently get tired of writing finite dimensional vector space, so I may abbreviate that capital FDVS, has the same length. That's theorem 214. And we've really proven this already, but now let's start writing some of this down, slowing the pace down a little bit. But we can say that we've effectively already shown this. The result of this theorem, or the statement of this theorem, we know, one, that a finite dimensional vector space, so any FDVS, any finite dimensional vector space has at least one spanning list. We can find a spanning list for any finite dimensional vector space. Two, the length, and now we know what length means. That means the number of objects in that list. The length of any basis is the same as the length of the shortest spanning list. Combining those two, the fact that we do have at least one spanning list for any finite dimensional vector space, and the fact that the length of the basis of that, or the length of the basis for that finite dimensional vector space, is the same as the shortest spanning list, that allows us then to say that therefore all bases of V have the same length. And that's what we were trying to show, that each of these bases have the same length, or any basis of a finite dimensional vector space has the same length. We can now use that to actually produce a definition for dimension. Here's a definition that we will use. The dimension of a finite dimensional vector space is defined to be the length, and we now know what we mean by length, to be the length of any basis. We know what it means to be a basis of a vector space of the vector space. Let's look at some examples of that. The first one, that is the one that we said would be nice if it was true, and indeed it is, the dimension of an n-dimensional vector space is n. What about the set of nth order polynomials? Not sure that you're going to like my notation, but I'm going to try to write down this sort of script P, and I'm going to say that it has order m with this subscript m in this field F. That actually has a dimension of m plus 1. And you can see that, and we'll give some more examples of that in a minute, but let's look at another example before we get into some polynomials. more polynomial examples. Another important example or illustration is that if we look at the dimension, and I may capitalize this or use lowercase for the d, if we look at the dimension of C, this complex plane, that's dimension 1, or C of the dimension of the complex number C, but the dimension of R2 is not 1, but it's actually 2. And if you look at the set of complex numbers, that you can think of as having a real component and an imaginary component, and so intuitively that seems like it's two-dimensional. R2, the real space of the plane, that is two-dimensional. So what's going on here? That's why I have these three question marks. Both of these sets, the complex numbers and R2, both are equivalent to the xy plane. If that's true, how can the dimensions be different? And it all boils down to the scalars that we're using in those two lists, or in those two sets, the complex numbers and this R2 space. For example, if we look at the two-dimensional plane R2, we can think of a basis consisting of two vectors, v1 and v2. And you could have all sorts of spanning lists that make up a basis for R2. The standard basis would be v1 equal 1, 0, v2 equals 0, 1. And we know that we can now take the span of those by looking at this linear combination of a1 v1 plus a2 v2. But now these variable scalars are an element of the real line, R. And for that reason, now this particular combination of a1 v1 plus a2 v2, that is sufficient to build or create or construct any element in R2. However, if we look at what's happening with the complex number C, we actually have just one element in that list that is capable of spanning the entire set of complex numbers, and we could call that V1. So now we have, and V1 could just be 1. But now this combination, linear combination of scalar times the vector AV1, if we now let that scalar A1 be a complex number or belong to the set of complex numbers, then that A1 times V1, a number V1, which could, as I said, be 1, then that is actually sufficient, this any arbitrary number a1, an element of the complex numbers, is sufficient to also build or get to any other element in the set of complex numbers, to construct any element in C. And that's why we can actually have this discrepancy or distinction between the dimension of C being 1 and the dimension of R2 being 2, even though they both effectively are covering the xy plane. Let's now look at some concepts related to, or some examples dealing with polynomials and dimension. Let's recall that this set of second order polynomials that have coefficients belonging to the real line, we can write that as a sub 0 plus a1x plus a sub 2x squared, where the coefficients, need to make sure I get my subscripts in the proper set. We now have a sub 0, a1, and a sub 2, as well as r can take on any values in the real number line. Now what we might like to know is, what if I take some vectors and ask if indeed they form a basis of this set of second order polynomials? So here's the question that I'm asking. Does v1 of x, which let me define as 1 plus x, v sub 2 of x, let me define that as x squared minus x, and let me define v sub 3 of x as 2. Does this set of vectors, so now I have, or list of vectors, I'm now looking at v1, v2, and v3. Does v1, v2, and v3 form a basis of this collection of second order polynomials coming from having coefficients belonging to the real line? And we really need to answer two questions. Does this set of vectors, v1, v2, v3, is that set linearly independent? And two, does that set span all of this set of second order polynomials? To see if it's linearly independent, what we're asked for then is, if we combine a1 v1, a2 v2, and a3 v3, can we find coefficients that are non-zero for a1, a2, and a3 when multiplied by v1, v2, and v3? Can we find coefficients that will allow that combination to equal 0 that are not equal to 0? If we're forced to conclude that the only way that this combination, linear combination of vectors v1, v2, and v3 is equal to 0 is to have the coefficients, or these scalars, a1, a2, and a3, identically equal to 0, then this set of vectors v1, v2, and v3 are linearly independent. Let's just mechanically write down what we have. We now have a1 plus v1. v1 was 1 plus x. We have a sub 2 times v sub 2, and that's now, v sub 2 was x squared minus x. And we also have a sub 3 times v sub 3, which was 2. And we want to know, can we find non-zero values, or the only way that that equals 0 is for those a's to be identically 0. Then we know the v's are linearly independent. Let's now just group coefficients of like powers of x. If we look at the powers of x, x to the 0, we have a1 plus 2a sub 3. So I could be explicit and say that's x to the 0, plus what coefficients scale x? We have a1 minus a sub 2 times x, and then we have a sub 2 times x squared, and that's, we're saying, equal to 0. Now, the only time we want to see if this is 0 for all values of x, so for this to be true for all values of x belonging to the real line, that's going to require that, in fact, a sub 2, the coefficient scaling x squared, a sub 2 needs to be 0. We also need a1 minus a sub 2 to be 0, but if a sub 2 is already 0, that says that a1 needs to be 0. And finally, if a1 plus 2a sub 3, that needs to be 0. And if a1 and a2 are already 0, that's implying that 2a sub 3 needs to be 0, or that a sub 3 needs to be 0. And now we've shown that for this linear combination of the vectors v1, v2, and v3, for that to equal 0 for all values of x, the only way that can happen is for a1, a2, and a3 to be 0, which says then that these v's are linearly independent. Now we need to check on the span condition. Now we can say, okay, what happens, or how effective are these vectors at spanning this space, this vector space containing the second order polynomials? In this case, again, we can look at this linear combination. We have a times v1, and that now gives us, let me change this a little bit so that I now am looking at this collection. I now have a1 plus a1x plus, let's say, b1 times x squared minus b1x plus 2 times c1, and that now needs to hold for all of these a's and b's. Now we only have the one b1, and we only have the one a1, don't we? So let me not get carried away with what I'm doing here. We now have a1, we have b1, and we have, so if I look at what we have, and c1. And again, if we now start combining like coefficients, we have a1 plus 2c1 plus a1 minus b1 x plus b1 x squared, such that a1, b1, c1 are identically, or anywhere in this real line. And I hope that it's now clear that that's capable of spanning any of the coefficients, the constant coefficient, the linear coefficient, and the x squared coefficient. We can find a b1. Once we found a b1, we can find an a1 for the linear coefficient. Once we've found the a1, we still have flexibility in the constant coefficient by the choice of c1. So this now is equivalent to a gamma 1 plus a gamma, maybe I should say gamma 0, gamma 1x plus a gamma sub 2x squared, such that gamma 0, gamma 1, and gamma sub 2 belong to the real line. So this set of vectors, v1, v2, and v3, spans this entire second order set of polynomials, and now we can say that v1, v2, and v3 are a basis for P sub 2 of R. Another example, playing with polynomials, let's not go quite so elaborate. Let's just look at first order polynomials, which says that now we have this set a sub 0 plus a1x with a sub 0, a1, and x belonging to this field of real numbers. Now we might say, does the following vector v1 of x equal to 1 plus x, does that form a basis of P1 of the reals? I think it's clear that that's linearly independent, meaning if we looked at the linear independence of this, we would be looking at a linear combination of some scalar times v1 of x and asking for all values of x in v1, when does that equal 0? And that's only going to be true. So now we have b1 times 1 plus x equals 0, or b1 plus b1 of x is equal to 0. And the only time that that's going to be 0 for all x belonging to the field of real numbers is when b1 is equal to 0. So that is actually a linearly independent vector. It's just one vector. It should be independent, so it should be linearly independent. Now what we need to know is, does v1 span the set given by a sub 0 plus a1x such that a0, a1, and x all belong to the field of real numbers? Is it possible then that the span of v1, which is c1 v1 of x, which is now c1 plus c1x for all c1 in the reals, I hope that it's clear that that's not the same as this set of a0 plus a1x such that a0 and a1 are in the set, or in this field of real numbers, because now a sub 0 and a1 are independently selectable, whereas in v1 we can't adjust the constant coefficient and the coefficient of the linear term independent of each other, and for that reason we cannot cover or span all of this one-dimensional or first order set of polynomials in X. For that reason then, v1 of x is not a basis of the set of first order polynomials. And you could look at other examples to help you with that. Let's finish up by looking at some properties, and these I'm just going to simply state, and you can look at their proof and definitions or examples. You can come up with examples or think about examples by looking at the pages in Axler. Let's look now at proposition 215. That says that if this vector space V is a finite dimensional vector space, and let's say U is a subspace of this finite dimensional vector space V, then the dimension of U is less than or equal to the dimension of V. So any subspace, the dimension of that subspace of a finite dimensional vector space has to be less than or equal to the dimension of the contained or containing vector space. For example, if we had V equal to our standard three-dimensional space, and if U is now equal to the xy plane, then we know that the dimension of U is 2, and the dimension of V is equal to 3. And so we see that a subspace, which the xy plane is a subspace in R3, the dimension of U is now going to be 2, and that's less than or equal to the dimension of the containing vector space, which was third 3. Let's now look at proposition 216. Again, dealing with dimension. Given a spanning list, and we know what a spanning list is, that's a list of vectors that span the entire space, or given a linearly independent list of vectors, let's say in a finite dimensional vector space V, if that list, either a spanning list or this set of linearly independent vectors, if the list let's say, is of length n, or maybe I didn't define n, did I? So let's say if the list is of length equal to the dimension of V, then that list of vectors forms a basis of V. So you can now look at a spanning list or a list of linearly independent vectors. If that list has a length equal to the dimension of V, then that list of vectors is a basis of V. One more. Let's look at Theorem 218. Theorem 218 now says if V is a finite dimensional vector space and U1 and U2 are subspaces of V, then we can relate the dimensions of these. Then the dimensions of the sum of those two subspaces is equal to the dimension of U1 plus the dimension of U2 minus the dimension of U1 intersected with U sub 2. And that's a nice property or relationship that allows us to sort of quickly determine the dimension of the sum of two subspaces, or if we have an intersection, a non-zero, or a intersection of those two subspaces having a non-zero dimension. And that's what I would like to end with, this following observation or note. If the finite dimensional vector space V is a direct sum of two subspaces labeled U sub 1 and U sub 2, then the dimension of U1 plus U sub 2, which is actually going to be the dimension of V, is the sum of those two subspaces dimensions separately. We don't have to worry about their intersection. And the reason is since the dimension of U1 intersect U sub 2 is equal to 0, and that's from an earlier proposition, which is proposition 1.9 in the textbook, which says that in a direct sum combination of a vector space, the intersection by definition of those two subspaces has to be the origin or the additive identity, and that has a dimension of 0. That concludes this presentation on, or this session on, dimension.